Alright, hell yeah. So many people have seen this demonstration where you have this box plus this box equals this box. The most important part is you have to give your hypotenuse some sort of length. You can call it whatever, but we're going to call it a unit of 1. And with this angle, this is going to be the sine component. And if we make a square box, this is going to be sine theta, this is sine theta. Therefore, sine theta squared. Same thing here. This is the cosine component of this hypotenuse. So this is 1 times cosine. This is 1 times sine squared. When you add these, hey, it just happens that you get this area of 1. So what we're going to do is a linear demonstration of this. And it's pretty cool because what we're basically doing is we're turning this, always put a 1 out here because, hey, we're still dealing with a unit triangle. And I think that's the trickiest thing about not giving your hypotenuse a greater value than 1. Like bringing it down to 1 can be kind of confusing because then that 1 never shows up in front of whatever you're using. So hell yeah. So if this is 1 and this is the angle, well cool. This is the length of 1, so the length of this side, draw some sun shining rays, so this one's going to be 1 sine theta. That's this length right here. And this length right here is going to be 1 cosine theta. So the cool part about this video is we can take this and kind of break it up into two different operations. We can say, hey, this is the same thing as 1, and then we're going to be multiplying it by sine theta. That's the first thing we're going to do. And then we're going to pop out a number, and then we're going to multiply it by another sine theta. And so check out what we do even to this one. We treat this one as the hypotenuse, as it is, and then we multiply it by sine theta. And my take-home point is always think of sine theta as a percentage. Even though they call it like a fraction, this divided by that, the opposite divided by the hypotenuse is sine theta. But if you think of it as a percentage, you're like, oh, sweet. So we break this up. This looks like about 50%. You know what I mean? So maybe this is about 75%. I don't know. So this looks about 70% of the hypotenuse just visually. And if I say, hey, this is 100%, I don't know, this looks about, maybe 80%-ish. And maybe this is like 60%. So there you go. Alright, so sweet. So what we do here to get this length is we take the hypotenuse and then multiply it by the sine of this angle as a percentage. Sweet. So that was the first operation that we did, and we get this length. The next thing we're going to do is multiply that by the sine of the angle again. So what we do is we treat this as our hypotenuse. And the cool thing that we can do is we can just come off here as a 90. I made a separate video on this kind of as a, maybe I'll link it in the description. It's a very quick visual proof, but it shows that this angle is theta. And we're going to go over it a little bit slower. The fastest way to get here is be like, okay, this is a 90-degree angle. This is a right triangle. All these angles have to add up to 180. And so, if you want to write it out, say, every angle in here has to add up to 180. So we're going to start with this. We have a 90-degree right triangle plus theta. And then maybe you just didn't know what that is. You know what I mean? So just make it a variable and then solve for it. And what we're going to find, just the fast solution, is that, hey, if all three of these angles had to add up to 180, we always know we're dealing with the right triangle if it is right. So these two have to add up to 90. And, and we're going to show just in a second that this has to be 90 minus theta. So that's the one trick that you want to just be able to kind of spit out. And we're going to show it right here. So if we solve for this angle, cool, I'm going to get this angle to this side. And we're going to have 180 minus 90 minus theta. So I just got those two to the other side, and then I just flipped the equation. And so that angle is 90 minus theta. All right, so we have a check on reality that this is 90 minus theta. But we can slow it down again too. If that angle is 90 minus theta, and we have a 90-degree angle right here, hey, do the same game. We have 90 degrees. Has to be both of these angles added together. I don't know what this one is, so I'm going to say, hey, the angle I don't know plus 90 minus theta. All right, sweet. So let's get this to the other side. That's going to be 90 minus theta is equal to something we don't know. And you have to FOIL this through. So this is going to be 90 minus 90. And then it's just going to be plus theta. Okay, so those two cancel, and that angle is theta. So just the fact that you have to subtract things and maybe, but yeah, that's like, I still visually can't say like, hey, this is theta. I can see that this is 90 minus theta. But then if I have to say this angle is 90 minus this, I guess I can now see that in my head. I'm going to be 90 minus this 90. And then a minus, this becomes positive theta. Sweet. But just the idea is that this, so where we are in the steps is that we took this hypotenuse of 1. We found its sine component. And again, like the take-home point is like, hey, we're not doing this as areas. We're just doing this as a linear interpretation. We're saying, hey, if this is the hypotenuse, this is the length that we get after multiplying by that first sine theta. And then we're going to treat this as the new hypotenuse and then multiply it by sine theta again. And how we treat this as a new hypotenuse is we find that angle theta off of this line and then just drop down to 90. So booyah, this is a right triangle. Here is the hypotenuse. And so therefore, if I took this hypotenuse times sine of this angle, I would get this length. All right, booyah. So, and we're done. So that is the length that we get if I take 1 times sine theta times sine theta. All right, now we just do the process on repeat for cosine, and we'll see if we if it's fairly easy. So if I take 1 times the cosine, so that's what I'm going to do first. 1 cosine theta, that's the first operation I'm going to do. And then I'm going to make that into a hypotenuse, and then also take its percentage from an angle cosine, the cosine of that angle. All right, so this first one is the hypotenuse of 1. The cosine of this angle is this length right here. Okay, sweet. And then I take this as the new hypotenuse, and then I have to take the cosine of this angle. Well, this one is a little bit more straightforward, just to pop it down right there. And here's the hypotenuse. We drop down a 90, so we have two components of a 90-degree triangle. Here's our hypotenuse. This hypotenuse is this number right here. Cool. And we're going to take the cosine of it. If here's the angle, sun is shining, this is the sine component, this is the cosine component. And booyah. So there you go. So that is taking the hypotenuse of 1, cosine of the angle, to get this, treating it as a hypotenuse, taking the cosine of the same angle, booyah, and we get this length. And now you can visually see that this length plus this length is 1. You know what I mean? And the other way to write this, and that's kind of how we'll end it, because I just said, like, hey, unit triangles are the worst, because you're never going to see this 1 out here. You know what I mean? So it might be also, anytime you write down this equation, also write, hey, hypotenuse times sine squared theta plus hypotenuse cosine squared theta is equal to hypotenuse. Because if I said this was 100 and then the hypotenuse is 100, well, this is going to be some percentage of 100, and this is going to be some percentage of 100, and when you add these up, the percentages are going to add. So that's pretty sweet. So heck yeah. And I guess what that's saying is if you just take the sine of, if you have this hypotenuse as 100, and then you take the sine component, cool, this sine component added to this sine component does not add back up to the hypotenuse. But if you take this component and square it, hell yeah, and then this component and square it, they get bigger. But if you, that's going to, and you sum those together, it's going to equal to the hypotenuse squared. And if you treat your hypotenuse as 1, it's easier to see. Because let's say this was 0.6, percent. We said this was maybe like 60%, and this was 80%. Let's see if that even jives. Because if I said that this component was 60% of the hypotenuse, and this is 1. And that's also just saying this length is 0.6. And this length would be 0.8. So what we're going to do is we're going to square that number. And if we square 0.6, we get 36. You know what I mean? But we get 0.36. And how you would do that is 6 times 6 is 36. But we got to move the decimal place twice. So we get 0.36 there. Same thing here. 8 times 8 is 64. But we got to move the decimal place twice. So 0.64 plus 0.36, 6, 7, 8, 9. Hell yeah. And then that's exactly 1. And yeah, it is so bizarre that obviously, yeah, if this a 60%, 80%, 100% is the same thing, or is the same thing as a 3, 4, 5 right triangle. If this is 4, this is 3, because if this is 10, this is 6, and this is 8, which also makes, if this is 1, this is going to be 6/10, this is going to be 8/10, which also means that this, if this is 1, this is going to be 0.6, 0.8. So hell yeah. I mean, I wanted to make this video in a minute, you know, and maybe we will, just kind of a fast, but I think this was pretty good. This was a pretty good visual proof. You know, I just came up with this one yesterday, and I don't think it's ever been done, so I think the title will stand however I call this. So hell yeah, it's a linear definition for sine squared theta plus cosine squared theta. And I'm going to talk about the usefulness probably in the next minute, because like I really enjoy watching, especially, you know, just watching lectures, whether it's like Harvard, MIT, just kind of watching their physics lectures. And a lot of the professors will throw an equation on the board, and it usually involves some sort of sine or cosine. And the reason it does is because, you know, we have vectors like forces. You know, a force might be like in this direction. Well, the only way to make it useful is if you kind of take components, because then you can add them. You know, they're vectors. That's the whole idea of linear algebra. You know, the ability to break those components up, add them, and then get a result. And so, what was I going? Yeah, so just a lot of the equations, you'll just see a sine, you'll see a cosine. Sometimes you'll see a sine squared, a cosine squared. And this is just kind of a visual where if you see a sine in an equation, well, you just know that's a percentage of whatever number came before it. You can treat that number as your hypotenuse. And in a lot of physics problems, hey, if you have a force vector, hey, that is going to be your hypotenuse. You know what I mean? And then you're going to maybe want to break it down into like an x, y coordinates. You know what I mean? So those are going to be your components of it. So then if I, you know, this component would be the magnitude of that vector, you know, times the cosine of this angle. Cool. And then, you know what I mean? And we just showed that if it's cosine squared, you can still just say, hey, whoa, you know what I mean? Hey, maybe that's same angle, dropping it down, making this the hypotenuse, and now this is the magnitude of that vector, cosine squared of that angle. Hell yeah. Cool. All right, so, but yeah, just again, when you're watching problems or you see equations that involve sine and cosine, I think it's very useful to think of them as a percentage of the number that came before them. And especially when, you know, looking at identities, that they're never going to put that number 1 in front of, you know, just if you just see a sine theta sticking out there and then there's nothing in front of it, you can visualize, you know, a hypotenuse. And I think that's useful. It's always a percentage of something. You know, if someone's writing sine or cosine, then they are making a relationship between the thing that they're kind of analyzing and, you know, and a hypotenuse. And so, hell yeah, that hypotenuse would just be right out in front as that unit of 1. Cool. All right, so that's about it. So thanks for joining me on this one, and that's the video.